Okay, we're continuing on with the basic vector skills. So we're on number 5. Prove that the triangle inscribed in the semicircle is a right triangle. So that's actually a concept you learned back in Math 9, circle geometry. So we're going to prove that using vectors. There's different ways of proving it, but based on this diagram here, we can see that a vector is set up from the origin. On mine, it looks a little bit off, but it's a semicircle, so that origin needs to be a little bit over to the left. But we could call this, just for simplicity, call that vector A, going from the origin out to point A, and then lowercase b, and let's call this C. So we want to prove that that angle is 90 degrees. So we're trying to prove that vector AC is perpendicular to vector BC. Okay, so basically, if they are perpendicular, the dot product will be 0. So we're not going to say it's 0 right now. We're going to find the dot product of AC and BC. Basically, we want to know what it is. If it's 0, we know they meet at 90 degrees. Okay? So dot product will equal 0 if, right triangle means this, and if vectors meet at 90 degrees. Which would then make the triangle a right triangle. Okay, so ABC would be a right triangle. Okay, so for simplicity, we'll, as I said, use the lowercase arrowheads at C, so it's vector C minus vector A. BC arrowheads at C, so it's vector C minus vector B. Distribute the dot products. Okay, so we've got 3 vectors of this in terms of. Let's simplify that a little bit. So vector B here, you can see is, if this is the center, it's going to be the radius of the circle. So B will equal the opposite of A. Magnitudes of all of these will be the same. That might help us in a bit. So this here, B is negative A. Okay, and then you can simplify the negatives, but what you need to remember, if you're taking the dot product of a vector with itself, we talked about this before, the value of it is the magnitude squared. So say, for example, so if we're doing C dot C, that's magnitude of C, cosine of the angle in between them. Well, the angle in between them is 0 degrees, right? So this is going to be cosine of 0 degrees. Well, cosine of 0 degrees is 1, so, and that's going to apply to any that have the same. So this is going to be magnitude of C squared. This is going to be plus A dot C minus A dot C. Doesn't matter the order. And then minus magnitude of A squared. So those go to 0. Okay, then we have just stated that the magnitude is equal. So A equals C, magnitudes. So this is magnitude, that substitution, so it equals 0. Okay, so therefore, AC is perpendicular to BC. Therefore, angle C is 90 degrees. Therefore, triangle ABC is a right triangle. All right. Next one, proving the cosine law using vectors. Okay, so different ways of doing this one as well. You might see one way, I think on the solutions, I use the sum of the two vectors. In the video here, I'm going to do the subtraction of two vectors. I think it might be a little bit faster. So if we just draw a diagram, so let's call this V and this W. Oh. All right, so then when we join this up to form a triangle, then this is going to be W minus V. And so we want to get a relationship between the sides. Basically do kind of the opposite of what we did in the first part. I'm going to call that angle between the two vectors theta, okay? And we want to look at the relationship between the sides in this and come up with the cosine law. So we have to pretend that we don't know it. So how we did it without vectors was we split it into two right triangles. So here, I'm going to split this into two right triangles. Then use what we talked about yesterday. So we're given V and W. This vector here is vector V projected on W. So it's the projection of V on W. This would be the projection of V on the height, or on a vertical. You can call it V on Y. I'm just using height H to represent the height. For me, it just makes a little bit more sense. Okay, so that projection, so if this vertical went further up, and you can kind of think about it more, if it was over here on the left, and then you're projecting that from the right, then it ends here, and it's that vector is the same here. So that height vector is V projected on vertical. Okay, so you can call it V on the y-axis if you wanted. However you want. Now we want to get the relationship between the sides in both of those right triangles. So we know the magnitude of V squared is in Pythagorean theorem. That's for the left triangle. For the right triangle, or the right-hand side triangle, okay, so now what is this here, this vector? Because we don't want to use projection of W minus V. We don't know what that is yet. So it's really the magnitude of W minus the projection of V on W. Okay. Now, just like we did back in, I guess it was math 10 for you guys, cosine law, we want to solve for the height. Okay, so here I solve for that. So I'm just rearranging. I'm rearranging here. Okay, and now make those equal to each other. now I'm going to expand out. So that would be minus 2 times a negative is a plus. And then plus minus. Okay, so now you will notice I can get rid of these. And I want to solve for that side opposite theta. So that's the W minus H. So I'm going to show that. Oops. From the left, so then I would have V squared plus W squared minus 2W V. Okay, getting close, right? Then, if you take a look at your diagram, compared to theta, so VW is the adjacent, so cos of theta is projection over the hypotenuse V. So if we solve for VW, okay, and then we just replace it. Let's put in alpha order. And that's the cosine law. Done. Okay, so last one here, prove that statement using a geometric proof and then an algebraic one. We'll do the geometric to start. So again, let's draw our little diagram here. Like that. So we need 3 vectors. Like that. Oh. And then, sorry. So 3, I'm just doing 3 different size ones, different directions, just to make it a little bit easier to distinguish. So I'm going to use UV, well, we have to use UV and W. We're not told that U is a unit vector, so we have to assume that it's not. Okay. And some definitions of the angles in between. So we're going to go the angle between U and W, let's call that theta. And then the angle between V and W, let's call it alpha for now. Okay. So I'm going to start with the right-hand side. So, because then I don't have to do any adding of vectors. Okay, so my right-hand side. Okay, so geometric version proof. So we're using the geometric definition. So this will be U W cosine the angle in between them. That one is theta. And V W cosine in between those is alpha. Magnitude of W is common. Okay, so then let's take a look at this. So if we were to draw the triangle down to U, so U cos theta is going to give us this vector here. Well, talking about the projections, that vector there is U projected onto W. So we can really replace this with U, vector U projected onto W. Okay. Then for V, I've got in a different color down here, so magnitude of V cosine alpha, that's going to be this vector here, which is V projected onto W. Okay, and then those two together, what do they represent? Well, if we were to, remember what we're trying to show, like this left-hand side is a dot product with W. So somehow we have to show that this bracket is going to equal U plus V, the vectors, with that angle in between them. So if we add U and V, so here, let me put in here. So if I send that up here, then this vector here is U plus V. If I bring that down, then this whole vector underneath, right, this green one here, will be U plus V projected onto W. Okay? And so then, let's call the angle in between that another, let's call it theta. Okay, so then cos of theta equals magnitude of U, the projection of U plus V on W over the magnitude of U plus V. Okay. And these together, so take a look at the magnitudes of each of these. So U, magnitude of U on V, this one, so if I take that and the red underneath but put it tail to tip, it's going to get you the same as the projection of U plus V on W. Okay, so it's basically the same parts added together. So two things can happen now. This is the same as the magnitude of U plus V on W. Okay, and then based on that, we can replace, oops, I put the bracket in the wrong place. So now we can replace this with U plus V cosine theta. All right. We just rearrange that. You don't have to. Okay, then that's the definition of the dot part. So now this is the left side. Right, so the left side was U plus V dot product W. So by the geometric definition, I'll call the angle between U plus V and W beta, then it's the same. Left side equals right side. Algebraic proof is love algebra. Okay. So, you've got U plus V dot product with W equals U dot W plus V dot W. Okay. So, we're going to let U vector U be U1, U2, U3. V equal V1, V2, V3. W equal W1, W2, W3. So left side, we've got to add those vectors together. Dot product with W. Okay, so then we expand out, so that's U1 plus U1 times W1, V2 plus V2 times W2, V3 plus V3 times W3. Distribute. Okay, and then your right-hand side is U1, U2, U3, W1, W2, W3, plus V1, U2, W3, Okay, U1, W1 plus U2, W2 plus U3, W3. U1, W1 plus U2, W2 plus U3, W3. Okay, if it's not working out to be exactly the same order, then just rearrange. So I'll just rearrange. So the U1s, all the W1s, sorry, are together. That's what they are there. So now we've done that. And then the 2s. And that. And then the 3s. Left side equals right side. Done.